Okay, so nucleophilic reactivity, here we have quinoline at the alpha position. And it's going to, in this case, it's going to react. This is sodium amide. So that first arrow is not really a arrow pushing arrow. It's more of a coordination arrow, where the lone pair on that nitrogen is going to bring in, naturally want to kind of chelate to the sodium on sodium amide. There in that second group, you can imagine a base. Has mechanisms actually just not good. Just just ignore that middle structure there. Not a good intermediate. But the final substitution pattern product is correct. So we'll leave it at that. Never eliminate a hydride. That's just ridiculous. Okay, so lithiation, now we're seeing this is with isoquinoline, so that lithiation in Bewley is going to act as a nucleophile, and it'll add at the alpha position. This would actually be in lithium, right here, not NH. And then with the second equivalent of in Bewley, say you could deprotonate here, etc. And that's the end of our quinoline functionalization. So we don't have a lot of methods really. Typically, the way that you functionalize quinolines overall is that you bring in different starting materials to the synthesis. So the way that you get functionalized quinolines and isoquinolines is typically by using different substrates for your quinoline synthesis reactions. So you kind of do those quinoline synthesis last in your synthetic plan, and that of course adds a little bit of complication because those quinoline synthesis reactions are harsh. Okay, pyrazole and indazole synthesis. So pyrazoles and indazoles, they're used a lot of different places in medicinal chemistry. So they're not that common in nature. But a lot of synthetic medicines contain pyrazoles, pyrazolones, or indazoles. So, for example, Celebrex has a pyrazole, and we have inverse agonists for cannabinoid receptors, and other examples that we're going to talk about here. So we have some anti-inflammatory agents, and this is a multi-drug resistance inhibitor. So you use this in multi-drug resistant tuberculosis, and it's also anti-hyperglycemic. So that's too much sugar as opposed to hypoglycemic, which is too little blood sugar. And so you can see now again, these are privileged structures. these are privileged structures. So here's an example of an indazole drug by GSK, and this is an antiemetic to treat nausea and vomiting following chemotherapy. And this works really not, it's not perfect, but it works well enough that they learned a lot of indazole chemistry just for trying to make derivatives of this drug. It's actually the origin of a lot of indazole chemistry. Okay, so one of the common ways to make pyrazoles now is by using the Nor-pyrazole synthesis. So we use hydrazine, a 1,3-dicarbonyl, and we can get pyrazoles. So you can get a variety of pyrazoles. It's going to be a little bit dependent on the electronics of the 1,3-dicarbonyl, how the substitution patterns here play out. Okay, and then we'll go to the Nor-pyrrole synthesis slide.